Hello there, Mr. Sutton here, bringing you the Algebra 2 5.5 lesson on performing function operations. In this one, we will be performing arithmetic operations on functions, namely addition, subtraction, multiplication, and division. For our opening problem, they're asking us to find f plus g of x, given this f and g function, and also evaluate f plus g of 4. And then, finally, state the domain. We'll actually state the domain in between finding these two things. Just flows a little better. But that's what they're asking us to do here. So basically, we just need to take f and g, add those together, and get a new function out of it. And then whatever that is, plug 4 into it. And let's talk a little bit about this domain piece, though, because this can be confusing sometimes. So there's some big considerations that we want to do when we're doing domain, especially when there's radicals involved. So if you have radicals in the original functions or the modified functions, either way, you just have to make sure x is such that we have non-negative radicands. And we did this when we were doing the radical inequalities in the last lesson. So same kind of deal here. Also, in some of these, you might end up with variables in denominators. So denominators in either the original or the modified function cannot equal 0. So we also have to make sure that that's the case. And it is very important to make sure you're looking back at both the modified that you made and the originals, because if something doesn't work in the functions that went into making your new function, then it can't be part of the domain. So with all that said, pause the video and see if you can figure out f plus g of x, the domain, and f plus g of 4 for these functions. All right, since we're adding these functions together, we're literally just doing 3 radical x plus negative 10 radical x. These are already like radicals, so we can just add the coefficients 3 and negative 10. That adds up to negative 7, and then we have a radical x to go with that. And we're going to plug 4 in a minute, but let's talk about the domain. So we have these radical x's in the originals. So x has to be non-negative, so greater than or equal to 0. And just looking at the modified, we also still have the same radical, so that's not going to change from the originals. So our domain then is going to be x greater than or equal to 0, so non-negative. Now plugging 4 into this, we just have negative 7 times radical 4, which is just negative 7 times 2, or negative 14. On this problem, they're asking us to find f minus g of x, and then of negative 2, along with the domain. So pause the video, give this one a shot. All right, since we're subtracting, we're just doing all of this f stuff minus all of this g stuff over here. The first parentheses we can get rid of for free. For this next one, though, we're going to do negative x cubed. We have to distribute this negative everywhere, so this will become positive 3x squared minus 4x plus 2. And combining like terms just to make this a little less unwieldy, 3x cubed minus x cubed is 2x cubed. We have a negative 2x squared and a 3x squared. That adds up to 1x squared. And there's only one of these x's here, so negative 4x just stays the way it is. And then 5 plus 2, that'll give us a plus 7. So for the domain, the original functions were both polynomials, as is this modified function here. Polynomials always have a domain and range, if we're being honest. Well, at least a domain of all reals. The range could be different depending on whether it's an even or an odd polynomial. This one's an odd one, so it would also have a range of all reals as well. So all real numbers for the domain. And now we're going to plug in negative 2 to this modified function here. So we have 2 times negative 2 cubed plus negative 2 squared minus 4 times negative 2 plus 7. And let's see here. So this is going to be 2 times negative 8, which is negative 16. This is positive 4 plus 8, and then plus 7. This is negative 16 plus 4 and 8 would give us 12, so that's negative 4 plus a 7 is going to be 3. And there we have it. Now, one other thing that you could do on these problems if all you needed to figure out was f minus g of negative 2 and you didn't need the formula here with the x, is you could actually plug negative 2 into these functions individually, just evaluate them separately, and then subtract your results from that. So this isn't the only way to do it, but there's fewer places to plug in after you've simplified, so maybe not such a bad approach. For this next one, they want us to do f times g of x and then f times g of 9 for these two functions. So here we're mixing it up a bit. We have an x squared and a radical x. So initially we're just doing x squared times radical x. Now just as a little bit of a pointer on one of these problems, if you have radicals and you need to multiply them by other things, it's a good idea to convert radicals to exponent form in order to multiply them. So I'll let you roll however you want with that. So pause the video and see what you can do with this one. All right, so before I multiply these, I'm going to just turn this radical x into x to the 1/2 power. And then I can add these exponents together to get just one single term with an x. That's going to be x to the, let's see, this would be 4/2 plus 1/2, so 5/2. The domain on this one, this x to the 5/2 is still a radical. This is the square root of x to the 5th power. Since it's still the square root of x, it has the same domain as this g of x function, which is non-negative values. X still has to be greater than or equal to 0. This x squared doesn't have any limitations, but we're limited by the g function and what results from it. So now plugging 9 into this function, we've got 9 to the 5/2. I'll just turn this into radical form again to make it a little easier to evaluate. So this will be square root of 9 to the 5th power. Square root of 9 is 3. 3 to the 5th is 243. So there we are. On this next problem, now we're going to be doing division at the risk of being predictable here. So we have f divided by g of x, and 16 will be our lucky number that gets plugged into this new function. Pause the video and see how you can do on this one. This one's a little bit tricky, so be careful with that domain. All right, so we're just dividing the f and the g functions, so 6x over x to the 3/4. And it's probably a good idea to simplify this. We're going to be subtracting the exponents in this case. So this is 4/4 minus 3/4, or 1/4 to go with that 6. So 6x to the 1/4. And for the domain on this one, we have to be extra careful here. So the original g of x function, this was the 4th root of x to the 3rd. Since it's an even root, that means our domain is non-negative x values, so x would be greater than or equal to 0 because of the g function. However, once we divided these and put them in a fraction, once we have this x in the denominator, 0 is no good anymore either, because if I plug 0 into this, I would be dividing by 0. So because of this x in the denominator, we actually have to make our domain x just greater than 0, not greater than or equal to. So that's important to keep track of everything that's happening that goes into making this new function. All right, so with that said, let's go ahead and plug 16 into that. So we have 6 times the basically 4th root of 16. 4th root of 16 is 2, because 2 to the 4th is 16. And 6 times 2 gives us 12. For this next problem, they're asking us to use technology, aka Desmos, to evaluate, well, really all 4 versions, all 4 operations with f and g, plugging 2 in for x. So note that they're not asking us to actually write formulas for each of these. They just want to know the final result once we plug 2 into it. And they want that to 2 decimal places. So there's a couple ways you could approach this. One way you can approach these is to actually figure out, what f plus g of x looks like in terms of x, and then plug 2 in it. Or you could actually just split it up. So you have the option of writing your original functions in Desmos and just plugging the values in separately. For example, f plus g of a, you could write that as f of a plus g of a. And that would be another way to do it without even needing to figure out what f plus g of x looks like. So do it however you want. Pause the video and see how many of these you can find. All right, let's go to Desmos here. So let me begin by putting f and g in there. So we have f of x equals sqrt, square root of x. And then let me go down and do g of x as well. And that's going to be square root of 9 minus x squared. All right, so I'm going to just do a bunch of these. We're going to start with f of 2 plus g of 2. That'll give us the f plus g of 2. So f of 2 plus g of 2 comes out to roughly 3.65. Great. Next, for subtraction, we'll just do those things with subtraction between them. And if you've already got this in Desmos, this is the awesome part of this, is you can just change this plus to a minus. And now we have negative 0.82. Now we'll do f of 2 times g of 2. We'll just turn this minus into a time symbol, which on my keyboard is going to be Shift 8, the little star symbol there. So we've got 3.16. And then finally, f of 2 divided by g of 2. We'll just put a division symbol in here. Whoops. Let me try that another way. Let me do division, f of 2, g of 2. There we go. So I had to do a little more work on that one, and that's 0.63. Boom. So if you're doing this lesson as the CP non-honors version, then this is actually the end of the lesson. You can turn off the video if you like and try out that problem set. If you're doing the honors, we have a word problem in store for you, so stay tuned. For our final boss battle here, we're not going to battle the white rhino. I mean, how can you fight something that cute? We're going to talk about it though. So the heart rate and lifespan of one of these is related to the body mass by these two functions here. So as best I can tell, because they didn't really spell it out here, S is the lifespan, and we have R, which is the heart rate. So what does R times S of M look like, and what does it represent? So pause the video, and believe it or not, this one, well, there is a little bit of calculator work in here, but we're not actually plugging anything in. We're just getting the overall function. So pause the video, and let's see what that looks like. All right, so we are doing R times S, so 241 m to the negative 0.25 times all of this stuff. And we're going to multiply the coefficients together and then the m's. So let me go back to Desmos. And on here, let's do just a 241 times, we have 6 times 10 to the 6th, a little scientific notation for us. And that comes out to 1.446 times 10 to the 9th. We're going to leave it in that form. And now let's multiply the m's. Negative 0.25 plus 0.2. That should be negative 0.05 if we add those together. So there's our function. Now, what is this actually giving us? So what this represents, because we essentially multiplied heart rate and lifespan together, this is the number of heartbeats in the lifespan of a rhino with whatever kilograms this M weight value is. So lifetime heartbeats of a white rhino of mass M. Bet you didn't know that. So it's been a fun journey on this one. Because I'm the one in charge of this operation, though, I'm saying we're done here. So till next time, Mr. Sutton signing off.